Hello, everyone. Welcome to my talk. I am Jigao from the University of Virginia. I'm very glad to present our paper today. The title is Deletion, Inference, Reconstruction, and Compliance in Machine Learning. This is a collaboration work with Sanjam, Mohammed, and Prashant. Here is an outline of this talk. We will introduce two major threat models, deletion inference attack and deletion reconstruction attack. Recently, there has been more and more regulations about right to erasure. That is, individuals can request their data to be deleted. For example, GDPR in Europe allows consumers to delete their data, followed by many states in the United States. From this map, we can see a huge map of US are considering similar privacy regulations. We know that the machine learning models are built on user data, so upon a request from consumer, we will need to update the model, make the model forget this specific data, and this process is very costly. This fact motivates this line of work called machine learning. We briefly introduce this machine learning process here. Suppose we have a model H that is trained with examples E1 to E5. Now we get this request for deleting an example E4 in the dataset. The goal of machine learning is to get a new model. We call it HDEL. That is ideally the same as training a new model from scratch with the training set S, except this example E4. We call this ideal case as perfect deletion. We now pose a question. If privacy motivates such erasure requests, does doing this on learning really help the individual's privacy? This perfect model we get by retraining is built without this record E, so it seems to be unable to learn anything of E here. However, is that really the case? An adversary can observe both versions of the model. Here, the adversary already observed the model before deletion, and after deletion request, the model gets updated. The adversary queries the second model, and here's the problem. As a contrived example, suppose that our model returns the summation of records in a set. So for a single record, the model preserves its privacy to some extent. However, an adversary queried both models can then exactly infer this record E by just applying a single deduction. So in this example, the deletion operation totally destroys the privacy of the record. Come to our work, we study the privacy implication of this machine learning, and we make the following contributions. First, we formally define threat models, including the reconstruction and inference attack tailored for machine learning. And secondly, we also show some very simple attacks can succeed in these threat models for different machine learners. Specifically, we focus on two threat models. In the deletion inference attack, adversary want to infer whether an example is deleted or not. And in deletion reconstruction attack, the adversary wants to reconstruct the deleted example. Both threat models are very general, meaning that they have various forms and can be applied to many machine learning tasks. Before coming to our attack, we first introduce some related work on our topic. Salem et al. 2020 proposed privacy attacks on updated machine learning models. The model is updated with an additional example, and they train the generative models to reconstruct the example from the input for both model before addition and after addition. A concurrent work, Chen et al. 2021 proposed privacy attack on deletion. They adapt the memory inference framework by training an attack model from the output on the two models before and after deletion to infer whether an example is deleted. And comparing to these two related works, we give a new formal definition of privacy in various new settings. Also, we propose extremely simple but effective attack on both inference and reconstruction scenarios. We also present some partial theoretical justifications of why these attacks work and study attacks on new models such as language models. There is also a very recent work studying managing inference on model update with access on updated models. Now we start with deletion inference attack. We start with the deletion inference attack. First threat model we introduce is deletion inference, which is inferring whether an example is deleted or not. So here in the slides, an adversary wonder whether an example in E is deleted. The adversary get to query the model before deletion, and then query the new model after deletion. Note that the sequence of the query is fixed, because after the deletion, the original model is not accessible anymore. To clarify one thing here, the adversary knows the deletion happens, but just wondering about what is deleted. To highlight that, we study a more basic scenario, which is inspired by the indistinguishability security games in crypto, such as in CPA or CCA security. In the scenario, the adversary is given two choices, E0 and E1, and need to find out which one of them is deleted. We now formally define the security game of deletion inference. There are two parties, a challenger and an adversary. The challenger first picks a dataset with size m. The challenger then picks two examples, EI and EJ, and sends them to the adversary. The challenger then trains a model with the learner. The adversary have Oracle access to this model before the next step. Then the challenger tosses a coin to delete one example between EI and EJ and get a new model. And after that, the adversary is given Oracle access to this new model. And finally, the adversary guesses which one among EI and EJ is deleted. The adversary tells challenger a bit 0 or 1 and wins if the guess is correct. We call a scheme row insecure against deletion inference if there exists an adversary who succeeds with probability at least row. So when row is half, it is trivial because the adversary can just flip a random coin to achieve that. Now, before introducing our attack, we first see one possible attack, which is reducing the problem to membership inference. Membership inference attack is the type of privacy attack that returns whether an input is part of the dataset or not. If we have a membership inference adversary that always succeeds, we can then use it to get the membership of the two examples on the two models, and then decide which example is deleted. It is because the deleted example loses its membership after deletion. Because of this reduction, inference attack is only interesting when it can beat this reduction. Now, can we define an inference attack that can leverage this deletion scenario? We propose a simple attack. The intuition is that the loss of the deleted example should increase because it is removed from the dataset. The attack is very simple. Just compare the difference on the loss, that is the loss after deletion minus the loss before deletion. So the attack first queries the model H and H-del with both examples E0 and E1. And then it gets the loss of the two examples, computes the difference for both E0 and E1. And finally, the model returns the example with larger loss difference. For evaluation, our goal is to evaluate our attack on large models trained on large dataset. Our baseline is the reduction to the membership inference attack from Shockley et al., one of the famous membership inference attack. They train an attack model with the help of auxiliary data from the same distribution. The problem is that the Shockley attack trains several machine learning models to attack. So to compare, we need to retrain all these models for each deletion, which is very costly. To alleviate this problem, we apply the multi-deletion setting. So each time, we pick a batch of 100 examples and delete all of them. We also pick another 100 examples inside the dataset but not deleted. Then we perform deletion inference for each pair of the examples across these batches. We test these attacks on two deep convolutional neural networks, a small convolutional neural network, small CNN, and a famous convolutional neural network, VGG19. We train these models on two image classification tasks, Cypher10 and Cypher100. We summarize the result in these four figures. Our deletion inference attack is the blue curve here. Our deletion inference attack has high success rate, even in the case when the dataset size is large. We show that the deletion inference can be done when the datasets and the models are large, and when a batch of examples is deleted together. Due to the time limit, please refer to our paper for more experiment results. This concludes our result on deletion inference. We now move on to the second type of attacks, deletion reconstruction attack. Deletion reconstruction is a harder task. Suppose example E is deleted, and the adversary tries to reconstruct example E from the query. Deletion reconstruction attack is a stronger attack that can reduce to deletion inference. As if someone can reconstruct the example, they can also compare it with the example given by the challenger and tell which one is deleted. We also work on a variant of these models. Please check our paper for variant of reconstruction that we call deletion label reconstruction. Similar to deletion inference, there are two parties, a challenger and an adversary. The challenger first picks a dataset with size m and train a model with the learner. The adversary has Oracle access to this model. And the challenger picks an example to delete and trains a new model. After that, the adversary is given Oracle access to this new model. The difference here is that in deletion reconstruction, the adversary needs to estimate the example and send back to the challenger. The reconstruction doesn't need to be perfect, and the adversary's performance is measured by some distance metric that measures the distance between the reconstructed example and the deleted example. Now I present a reconstruction attack that is based on the intuition that the output of the instances around the deleted example E are likely to be different after deletion. In that case, the adversary first composes a set of instances T, which can be obtained from auxiliary instances from the data distribution, or just random sampling from the input space. The adversary first queries the model with all the instances in T. And after getting access to the deletion model, it queries all the examples on the deleted model. The adversary then creates a subset of T, which includes all the instances whose prediction label changed as the deletion region T prime. The attacker then computes the majority of T prime. It is actually a meta attack because the majority here can be general. Adversary can choose an appropriate aggregation function depends on the task. An example on the majority function is that for each bit in the data, just take the majority vote of that bit over all the examples in T prime and returns a reconstruction based on that. As a test to the reconstruction attack, we consider a case when we want to reconstruct images for nearest neighbor predictors. We use OmniGlow dataset for that, which include 20 copies for handwritten characters. We use 10 copies of each character to learn a model, and the other 10 copies of each character to build an auxiliary support set T that is available to the adversary. Our deletion reconstruction attack reconstructed a lot of examples, which is shown in the row marked with 2. Comparing to the actual deleted example at row 3, they show a lot of similarity. And we can see that without deletion, the reconstruction basically reconstructs nothing. Please refer to our paper for more experiment results and details. As a summary, in this paper, we study privacy implications of machine learning. We propose 2 threat models, deletion inference and deletion reconstruction. And we show that simple attacks are effective for a variety of settings and models. For future work, one direction is to give optimal bounds on the deletion inference attacks. Another direction is to have provable attacks and defenses under update beyond merely applying differential privacy. That's all. If you are interested in our work, please check our paper for the details. Thank you.